How's exam one?
Good.
Easy.
Easy.
Value per question will be at least 12 points. Maybe more. But if you multiply 24 times 12, you'll get an earnable value that's a hell of a lot greater than the base value of 200. I do this for each quiz, each exam, as I have told you. And after I examine the results from exam 1, then I'll know what I want to aim at in constructing special quiz 1, which I expect to develop this weekend. That's the way I enjoy my weekends. Writing quizzes, writing exams, writing notes, doing chemistry. Ha ha ha. Should have this stuff up for you this afternoon. And I believe everyone has taken exam 1. So after I check to be sure, I'll also post the answer key. For those of you who took exam 1 earlier yesterday, I've got your exam paper here. Should you be interested in getting it back, which I hope you will be, see me right after our conversation today. Now we continue with considerations regarding determination of hydronium ion concentration for water solutions of polyprotic bronzed-Lowry acids. 3 categories. The parent acid is molecular and strong. We looked at this on Wednesday. Given that using the most common example of such, which is sulfuric acid molecule. And of course you recognize there were a couple of questions regarding that on exam 1. Next case, the parent acid is molecular, but this time weak rather than strong. You'll see that calculation of hydronium ion concentration for this kind of acid, or solution of this kind of acid, is the easiest. Why is it the easiest? Let's take a look. There's a detailed analysis of this calculation for quote-unquote H2CO3, or hydrated CO2, that's in the notes. So rather than repeat that, let's have a peek at analysis for a different weak polyprotic molecular Bronsted acid. There are a number of examples of such in the acid-base table. I picked on H2S. 10th molar to 2 sig figs. How do we get the hydronium ion concentration? As always, you got to pay attention to the chemistry which exists in the system in order to be able to recognize system PSI, right? If you don't know what you're dealing with, you can't do this. But if you know what you're dealing with, then you can. The first ionization reaction, the second ionization reaction. K for the first ionization reaction, 1.1 times 10 to minus 7. And in our acid-base table, you see HS minus listed in the acid column. You also see it to be listed as an acid weaker than water. Therefore, it has a Ka value, not Kb value, Ka value that's smaller than 1.8 times 10 to minus 16, which is Ka for water. It's been estimated as 1 times 10 to minus 19. And what you can do with numbers like this is to get pretty close values. Do you recognize why? Do you see the tininess of this number? So you're measuring very, very tiny molarities in order to get values like this by experiment. And that's not easy to do with with much reliability. But in any case, to continue, question. Parent acid, weak and molecular. Look at this huge gap in K values. This K value is 10 to the 12th, this K value. Somewhat over 10 to the 12th. It's only a trillion. Why is this the case? The same applies really to sulfuric acid solution, except that in that case, the first Ka is a very large number, which accounts for why sulfuric acid molecule ionizes, practically speaking, to an extent of 100% in water solution. When we get to chapter 21, we'll show you how to get Ka values for strong acids. For now, it's good enough for us to recognize that in the water solution of the strong acid, the ionization extent is 100%. But back to this weak acid. Ka1 is a small number, but it's huge next to Ka2. Why is this the case? Why is this the case, Professor Coulomb? You know about Professor Coulomb, don't you? My 2045 class, I argue strongly that Coulomb's law is the most fundamentally important law in the world of chemistry. Why do you think I say that? Of what are atoms composed? Protons, electrons, and neutrons. Which of these particles are charged? Protons and electrons. Which of these particles, in the main, determine the reactivity of an atom? The electrons and the protons, not the neutrons. Charged particles. All atoms are composed fundamentally of electrons and protons. You think Coulomb's law relates to the interaction between electrons and protons? Does Coulomb's law relate to the interaction between electrons and electrons? Are they charged particles? Then it relates. Now then, do you think it's easy to take H+? What's the positive charge density of H+? We talked about hydrated metal ions, for example. We recognized that metal ions with substantial positive charge densities like Al3+ and Fe3+ and others which you see listed in the acid-base table form defined hydrates because they have appreciable positive charge densities. And these defined hydrates, for the hydrated metal ions, show measurable Bronsted acidities. How does the positive charge density of H+ compare to the positive charge density of Al3+? Which has the greater positive charge density? Which of these two particles has by far the greater positive charge density? H+. Why? This thing is a damn nucleus. You learned in 2045 how the size of the nucleus compares to the size of the overall atom, didn't you? The nucleus itself is less than 0.1% of the total volume of an atom. So when you take the H atom and take away from it its electron and create H+, you got a positive charge sitting on a nucleus. Woo! The positive charge density of that is huge. That's why I'm not accepting any textbook that writes H+. Because damn it, if metal ions can form defined hydrates, you know damn well H+ is going to form a defined hydrate, the minimum of which is hydronium ion. Because the positive charge density of H+ makes the positive charge density of any metal ion look like nothing. This is just common sense. Yet these dummies who write these books still write H+ as an ingredient of a water solution. And they say, when I challenge them on this, they say, well, it's convenient. Ah, it's conveniently wrong. And we're trying to get these people to learn chemistry. So get that garbage out of your book. And they walk away. Martin Silverberg is the author of the book you folks use for 2045. Remember that? He sat in my office for over an hour listening to me rail at him about the junk that's in his book. Telling him why I have no use for his book in my class. He said, thank you, walked away. That was 8-10 years ago. He made no changes. Because he knows I'm a rare bird. The sad truth is that most of the people that teach this stuff don't want to bother with it. They don't. They want the textbook to carry the ball. And they come into class, and what is lecture? They mouth the textbook to you. What the hell good is that? If I taught from a textbook, I'd say, read the textbook. You'll see me when it's exam time. If you have questions, come to my office. Ha! But this stuff is wonderful. I would never violate the educational process with respect to chemistry and behave like that. In fact, anybody who behaves like that ought to be horsewhipped and kicked out of the university. Forthwith, boom, out, goodbye. You got no business being here, because this damn place was built for education, and when you do something that doesn't support that process, you don't belong here. You think I have an attitude about this? You betcha. But I'm very sympathetic with you folks. But I have no sympathy whatsoever for faculty who don't live up to their responsibilities of trying as hard as they can to teach this wonderful stuff. On we go. Gee, I got a lot of mileage out of that H plus consideration. And so, do you see, any acid-base reaction, Bronsted-Lowry, involves taking H plus away from the parent acid, doesn't it? We know this. That's what a Bronsted acid is. It's an H plus giver. Well, here you're taking H plus away from something that's neutral. Ha-ha! But when a molecular acid ionizes, you are then going to take H plus from something that's minus. You think that's easy to do? Coulomb? This thing with this huge positive charge density, you got to rip it from this to make this thing go. And also take note that the conjugate base of this is sulfide ion. So it's really sulfide ion you're ripping this H plus from when this goes. You remember where sulfide ion is in our acid-base table? One of the couple of bases in our table, stronger than hydroxide ion. Why do you think sulfide ion is such a potent Bronsted base? Why do you think sulfide ion holds so tightly to H plus? Coulomb. Because it has a huge negative charge density. How about that? That's what makes a base strong. Negative charge density. And so, that accounts for why. When you look at the second ionization or subsequent ionizations thereafter for a parent acid which is molecular, these K values get very small because you have to fight Coulomb's law. You have to fight the strong attraction that exists between H plus and the negative species from which you're trying to extract this H plus. Now then, we get to why calculation of hydronium ion concentration for a polyprotic weak molecular acid is easy. Since this second K value is so very small compared to the first K value, do you think we have to pay attention to the second ionization to compute the hydronium ion concentration? Do you think the second ionization with a K value like that is going any place? No. That's why it's easy. For a parent acid which is polyprotic, molecular, and weak, Ka1 is the only ionization equilibrium you have to focus on to calculate hydronium ion concentration correctly. We'll prove that in a moment. Now, back to this. Oop. I went on to the proof already. Back to this. If what I said is true, can you tell me at a glance with this K value of 1.1 times 10 to the minus 7 what the hydronium ion concentration is for 0.10 molar H2S? Because what we just told you is that this relationship applies to a weak molecular polyprotic acid, because we don't have to pay attention to the second ionization equilibrium, which means after this reaction goes, these molarities stay the same. Because if this reaction isn't going anyplace, this molarity of this doesn't change, and there's no contribution to the hydronium ion molarity made by the first ionization equilibrium by the second ionization equilibrium, because the second ionization equilibrium isn't going anyplace. So, there you have it. And as we've already recognized, if X is a small enough value, which it likely is, subtraction of X from M sub I does not change M sub I. And if that is true, then X is equal to M sub I times the Ka value, take the square root thereof. All right? So I'm taking the square root of 1.1 times 10 to minus 8. What is the square root of 1.1 times 10 to minus 8? I'm listening. Let's start with this part. Square root of 10 to minus 8 is 10 to minus 4. What have I got over here? Square root of 1.1. Oh, that's a tough one. There it is, 1.0. Now let's ask another question. If this be true, what is the sulfide ion concentration in this H2S solution? The sulfide ion concentration. Before we do any arithmetic, we know it's damn small. Now tell me the value for the sulfide ion concentration. Fill in the blank. Let this stuff talk to you. As this talks to you, it tells you. The only source of sulfide ion in the system is this second ionization reaction, right? Okay? So let's go over here and write 1 times 10 to minus 19 equals that. Okay so far? Because that's nothing but the equilibrium constant for this reaction. But we've said this reaction, practically speaking, goes no place. Which means for this H2S solution system, how does the hydronium ion molarity compare to the HS minus molarity? What do we find them to be from this calculation? They're what? They're equal. How about that? There's the sulfide ion molarity. It's Ka2. Statement. In dealing with a water solution of a polyprotic molecular acid, which is weak, the concentration of the species produced when the parent acid loses 2 H pluses. So from H2S, you lose 2 H plus, you get sulfide ion. Okay? The concentration of the species produced when the parent acid loses 2 H pluses is always equal to Ka2. That's it. You really don't have to do any calculation if you've understood this. Now then, students often ask, how can I be sure that this second ionization equilibrium, when the parent acid is weak in molecular, How can I be sure the second ionization equilibrium doesn't contribute? Now, it's rather obvious for the H2S solution, because HS minus is an acid weaker than water. Okay so far? Now let's look at hydrated CO2, quote unquote H2CO3. Because after that loses H+, I've got bicarbonate. And we know that bicarbonate is a stronger acid than water. In fact, it's a good deal stronger acid than water, right? We've talked about that before. You see such, or recognize such, from the data that's in our acid-base table. Ka for bicarbonate is 4.8 times 10 to minus 11. Now, Ka1 for H2CO3, or call it just Ka for H2CO3, hydrated CO2, quote unquote, is 4.2 times 10 to minus 7. Okay? But as we have reminded ourselves here, if it is true that we never have to pay attention to the second ionization equilibrium, if I want the hydronium ion molarity for 100th molar H2CO3, I just cross multiply m sub I times Ka for H2CO3 and take the square root. So I've done it. Okay? But now we get to this question which plagues students. This HCl3 minus thing is a stronger acid than water, a good deal stronger acid than water. Still a very weak acid. But since it's a good deal stronger than water, how can I be so sure that it's still not going to make a measurable contribution to the hydronium ion concentration? How can I be sure for a water solution of hydrated CO2 that I need pay attention only to the first ionization to calculate correctly the hydronium ion concentration? Are we understanding the question? Well, let's take a look at Ka2 for H2CO3, which of course corresponds, not Ka1, but Ka, to Ka for bicarbonate, which is 4.8 times 10 to minus 11. There's the Ka expression, isn't it? Okay. Now then, from the first ionization equilibrium alone, we've got this value for the hydronium ion concentration. Now, if the second ionization goes to a measurable extent, whatever it may be, the hydronium ion concentration has got to get larger than this number. If the second ionization makes any contribution measurable to the hydronium ion molarity, the hydronium ion molarity has got to be something bigger than this number. Nothing fancy about that. So let's pick, using two sig figs, the next value, which is larger than this number. It's 6.6 times 10 to minus 5, isn't it? Okay? 6.6 is larger than 6.5. And any other number bigger than 6.6 is larger yet. Okay? So at the minimum, if the second ionization contributes measurably to the hydronium ion concentration for this solution, the hydronium ion concentration will be bigger than 6.5 times 10 to minus 5, which means minimally it'll have to be at least 6.6 times 10 to minus 5. Well, if the hydronium ion concentration then is boosted to 6.6 times 10 to minus 5, what's carbonate ion concentration going to be? Let the stoichiometry of this reaction talk to you. What is it? Yes. You see where you got that? No, we don't see where we got that, did we? We went from 6.5 times 10 to minus 5 to 6.6 times 10 to minus 5. You agree with that? What did you have to add to 6.5 times 10 to minus 5 to turn it into 6.6? Times 10 to minus 5. What do you got to add? You got to add 0.1 times 10 to minus 5, which is 1 times 10 to minus 6. That means if this reaction goes, there's the second ionization equilibrium for this acid. If this reaction goes, so as to increase the hydronium ion concentration from 6.5 times 10 to the minus 5 from the first ionization equilibrium to 6.6 times 10 to the minus 5. Then this reaction has also created a carbonate ion molarity of 1 times 10 to the minus 6. Right? That's just stoichiometry. Because if this thing made 1 times 10 to the minus 6 moles per liter of hydronium ion, then it also made 1 times 10 to the minus 6 moles per liter of carbonate ion. Now the total hydronium ion is from the first ionization plus the second ionization. You've got to add them up. But from this reaction alone, to make the hydronium ion molarity increase from 6.5 times 10 to the minus 5 to 6.6 times 10 to the minus 5, this has got to make at least 1 times 10 to the minus 6 moles per liter of hydronium ion, which makes this at least 1 times 10 to the minus 6 moles per liter of carbonate ion. Okay? Now let's go back to this. If that is true, what will the equilibrium molarity of bicarb ion become? What did the equilibrium molarity of this start at before this reaction is considered? 6.5 times 10 to the minus 5, didn't it? So this got lower if this goes. To what did it become? What did it become? 6.4 times 10 to the minus 5, right? Because you lost 0.1 times 10 to the minus 5 moles per liter of this to make 0.1 times 10 to the minus 5 moles per liter of this. It's just material balance. All right? So these are the values which we would have for the components of that equilibrium constant expression. If this ionization equilibrium makes any boost at all to the hydronium ion concentration. Okay so far? Let's put these numbers in. 6.6 times 10 to the minus 5. 1 times 10 to the minus 6. 6.4 times 10 to the minus 5. Do you agree that 6.6 times 10 to the minus 5 and 6.4 times 10 to the minus 5 are about the same? All right, so we'll take the liberty of doing this. Here's the Ka value. You see that carbonate molarity? That's one hell of a lot bigger than this. So what does that mean? That means the true carbonate molarity for this system compares how to this? How does the true carbonate molarity compare to this value? It's a hell of a lot smaller, isn't it? Now tell me what the carbonate molarity is. There it is! Interesting, isn't it? See, what I'm trying to do is to train you how to let this stuff talk to you so that you will understand what this stuff means. That's not easy to do, but that's what it's all about. And that's the attempt that we are making. All right? So, 1852, 1853 to relate to the work we just did. In the notes, with the conversation that you see about the hydrated CO2 solution, the quote-unquote H2CO3 solution, for which Ka is 4.2 times 10 to the minus 7, you also see some commentary about the fact that when you dissolve CO2 in water, practically speaking, you get no true carbonic acid. Because true carbonic acid has been isolated and has been found to show a Ka value of 2.5 times 10 to the minus 4. And that's a whole lot bigger than 4.2 times 10 to the minus 7. 4.2 times 10 to the minus 7 is Ka for H2CO3, quote unquote. And 2.5 times 10 to the minus 4, right here, that's Ka for true carbonic acid. Well, if on dissolving CO2 in water, we made true carbonic acid, seltzer water and club soda be a hell of a lot more acidic than it really is. So by simple pH measurements, we recognize that dissolving CO2 in water really produces very, very little true carbonic acid. It produces hydrated CO2. as the pH measurements of seltzer water corroborate this. Again, if you got true carbonic acid when you dissolve CO2 in water, seltzer water will be a lot more acidic than it really is. But we can ask this question. Over here we considered 0.010 molar hydrated CO2. So for comparison's sake, I'll write 0.010 molar true carbonic. 100th molar hydrated CO2, 100th molar true carbonic. Which of these solutions would have the higher hydronium ion concentration? I just answered this, but what is it? True carbonic, a lot higher. I mean, it's got a much higher Ka value. Okay? Which of these solutions will have the higher bicarb ion concentration? True carbonic. Now watch out for this question. Which of these solutions has the higher carbonate ion concentration? And the answer is? Which of these solutions has the higher carbonate ion concentration? I asked this question in a dirty pool fashion.
They're the same.
Because they're the same. Ha! The carbonate ion concentration is 4.8 times 10 to minus 11. I don't give a damn what the molarity is of the carbonic acid parent solution. Right? Weak molecular polyprotic acid loses 2 H pluses. The concentration of the resultant species, like carbonate from H2CO3 or sulfide from H2S, the concentration of the species after the parent acid loses 2 H pluses is always equal to Ka2. We just proved it. That's what that does. All right? So now we're going to talk you through this phosphoric acid solution. I'm not going to write anything on the board for this. You can do the arithmetic as necessary for practice. This is question 1854. Now before we go further with 1854, please fix the incorrect Ka3 value that's in the notes. You'll see this correct Ka3 value in our acid-base table. It's 4.5 times 10 to minus 13. There's the parent acid, phosphoric. There's what you get after 1 H plus loss. After 2 H plus losses, and then after 3 H plus losses, you get the phosphate ion. And it is for this solution the phosphate ion molarity that we wish to determine. Now notice the phosphate ion is produced after the parent acid loses 1, 2, 3 H pluses, not 2. So for this solution, to get this, get this. You recognize at a glance you got to go to Ka3? Because you don't make phosphate ion until you get to Ka3. Okay? So we'll write this. Where's this coming from? For this solution, how do we get the hydronium ion concentration? What calculation do we have to do to get the hydronium ion concentration? Ka1, all done. So for this, we'll write from Ka1. So this is no longer an unknown. How do we get this molarity? What is it? This is Ka2. Bingo. Just write in the value, Ka2. So how many unknowns you got now? 1. Done. That's all there is to that. And now, 1 minute conversation on the real fun. The real fun is going to start now. Hydronium ion concentration for a water solution of a special polyprotic Bronsted-Lowry acid. Hydrated metal ion. Why is this special? This is special because not only is Ka1 for this. This is the iron-containing ion in that solution. Okay? Ka1 for this is 4.0 times 10 to minus 3. That's a pretty big value as far as Kas for weak acids go. And after this loses H plus, you got this. Ka for this is Ka2 for this, and Ka1 for this. And now we'll take a look at why this is very special fun. Ka2 for this, same as Ka1 for this. Is 5 times 10 to minus 4. Oh, 5.0. Why does this make this special fun? You see the difference in these K values? Is there much difference in these K values? Not at all. So guess what? In this case, the second ionization equilibrium does contribute. So when you write the ionization equilibrium reactions, you'll have two equations, and count them up. 1, 2, 3, 4 unknowns. Can you solve it? 2 equations, 4 unknowns. Can you solve it? Yes or no? No. Ha ha ha. So now comes charge balance. This is what we do next time.